Okay, so while everyone is sitting down, I'll blatantly plug the VM Tech Summit in the old world, which is a little bit more runtime-centric and a little bit less language and Java-centric, which we started doing by JFocus last year. It was very invoke dynamic-y then, but we hope to spread it out a little bit more subject-wise this year. For example, last year we also had Slava from the V8 team there, which was quite interesting. So we're trying to look at these kinds of runtime things as well. So I just wanted to advertise it here in the other place in the world where this kind of geeks hang out in one room at the same time.
It's a good party.
Good party. So Stockholm in February, I mean, it's awesome.
What's the temperature? What's the temperature?
Let's not get into specifics, but it can be windy and snowy, but usually it turns into slush really quickly and it's dark, so you don't need to.
But it's dark.
Yes.
It's supposed to be inside.
Yes.
Dark.
No, not 20, maybe 10. No. So, this is the last session. I'm closing JVMLS, and I will be talking a little bit about Nashorn for Java 9 and our execution model and how it changed, because we did a lot of performance work for Nashorn when it comes to executing programs quickly for Java 8260 in the optimistic type work that I presented last year. And we have to pay the price of stable runtime performance with startup time and bytecode generation, which we have heard various grievances of the slowness of at this conference. So I'm going to talk about 9, or a stretch goal for 9, how we pay back or amortize the cost for extra type computations. We'll get reset the timer here so I start on 0. So you all probably know me. I used to work for Oracle, and since I'm currently unemployed, but next work I'm starting as performance and service stack architect, performance architecture for Clara, which is an e-payment provider based in Stockholm, Sweden. It was just rolled out in the United States a couple of months ago. So we'll see. Sounds like fun, but I'm definitely going to miss this place. So as I'm unemployed right now, I don't really need the safe harbor statement. It just came in there with the template. So it's just always wanted to do that. Like you don't need any safe harbor statement for this presentation. Or usual rules apply. I might be lying anyway. So the agenda. Dynamic languages on the JVM, everyone knows about that and why, so I don't really need to spend a lot of time in it. Nashorn in general, performance, quick recap of the optimistic type work and measurements, and how we got near native performance for a lot of interesting scenarios with invoke dynamic on the JVM. And then startup and warm-up performance, which is the main topic of this presentation, and how we tweaked it, and how our new execution architecture looks like, or where we're going. And future work that this enables. So running alien languages on the JVM isn't something that should be a foreign concept to anyone in here. And I'm saying alien languages, not just dynamic languages, because anything non-Java is alien, both if it's like traditionally dynamic like JavaScript or something in between like Scala. So people have been deploying stuff that isn't Java as bytecode on the JVM since '95, and they keep doing it, and this is not something that is going to slow down now that we have invoke dynamic and MLVM projects actually running at full speed. So alien languages might seem like a cute concept, but when you work with JavaScript, it's more this kind of alien that we're used to. So me and Attila and Mikael and Hannes and several people here have wrestled aliens for a couple of years, and we've actually managed to get them to perform and do our bidding to a certain extent, which is fun. So it's always the same struggle there. People want the JVM because it's automatic memory management and it's JIT optimizations and native threading capabilities and all aspects of a runtime that don't need to re-implement if you just want to develop a language and convert it to bytecode and run it. There's the hybridizations. You have the entire JDK class library that you can access from your Java scripting classes. Which is also, I thought hybrid programming was something that's weird and slightly tacky when I first saw it, but I actually realized with projects like Avatar.js that it's extremely powerful if you use it for certain things. And we have all these man-decades of high tech in the JVM that you can fall back to.
Centuries. Programmer centuries.
Yes, programmer centuries even. And looking at like code bases for Rhino, Nashorn, Mozilla SpiderMonkey and Google V8, Java versus native implementations of JavaScript runtimes. I mean, this obviously shows that it's a good idea to write less code and still get the language. So the Nashorn project, also a very quick recap for whoever's on the internet. You're all intimately familiar with Nashorn in here, was the invoke dynamic proof of concept that the LangTools team started writing in 2010. Which was a compliant JavaScript runtime, or aimed to be a compliant JavaScript runtime to show that invoke dynamic was sharp enough for real use. Nashorn is open, it's fast, with this disclaimer asterisk there saying that comparable to performance in native implementations in domains where it matters, which means that we're getting good results on things like the V8 benchmarks and avatar servers that run Node workloads are similar to V8 workloads in a Node environment and so on. You got the scripting package so people can write their hybrid applications and extensibility through that. So long-term Nashorn goals, we've also addressed at various conferences, is we want to see if it's a toolbox for other dynamic languages, not just JavaScript on top of the JVM. For instance, this year I had a thesis student who did a TypeScript front end with relatively little effort running on top of Nashorn. So we're trying to expose things in Nashorn to be more and more platform agnostic for dynamic languages. We're already using the Dynalink library for call sites. We're looking a little bit at JRuby 9000, which excites us with the IR format is something that looks reusable and conceptually complete or near complete for several languages on the JVM, dynamic languages on the JVM. So we sort of want to provide some kind of invoke dynamic way of language implementation in the long run. So performance then, which is what I've mostly been spending my time on. What does performance mean? Performance time in any runtime is the sum of execution time, the time it takes to run your program, execute your program, and the rest, which I call runtime overhead here. It's like garbage collection, waiting for locks, generating the code that is to be run, anything not executing the program or performing the workload. And for 8U60, Java 8U60, we spent a lot of time getting execution time down. So invoke dynamic optimizations, working with the JVM, so invoke dynamic run faster, incremental inlinings after Java 7 for call sites within these, looking at field access times when we have variables in scope, how do we get them quickly, native code implementation, and for me I mean the libraries, the JavaScript libraries in Nashorn, things like array and string functionality and functions in JavaScript, implement them fast. The type specializations, because bytecode is strongly typed, we have to use as narrow a type as we can, as primitive a type as we can to get enough performance on a hotspot. Looking at the JIT, Roland's type optimization work, all this stuff that we've been concentrating on so far brings execution time down, generates faster code, generates better bytecode, and has the JVM generate better native code from the bytecode. So as of 8U60, we checked in optimistic types, which is there but disabled, which is a major overhaul of the model, how we generate code, how we generate bytecode for hotspot from JavaScript programs, using primitive types wherever we can and as narrow types whenever we can, because boxing reigns supreme if you just use the most conservative representation of bytecode for a dynamic language, which is objects everywhere. 8U40, yes. Yeah, I suck. 8U40. It's still disabled though, but it's there. So this brings us to runtime overhead, which is sort of stretch goal for 9, I guess. There is a JEP coming. There's actually 2 JEPs coming, and they haven't been published yet. And I'm cut off from Oracle, so I don't really see the status of that. But for runtime overhead, we're looking at increasing JIT speed, minimizing relinking of call sites and bytecode generation. Can we do tiered recompilation of the JIT, class installation speed in the JVM, like the compile units being classes containing a method is the minimum compile unit in Java, and if you like shuffle too many of those into the system, you get overhead. So especially startup and warm-up was very affected by optimistic types, since the optimistic types metaphor sort of works like guessing that we have a narrow type like an int for an unknown type that we can't statically derive. And then if we're wrong, we regenerate the class from a continuation point when we notice that we're actually overflowing or we're getting something back from memory that wasn't the int we sought after. So there's a lot of retakes in the optimistic type branch. Even though steady state performance is really nice, we added a lot of overhead getting there, warming up and starting up. So, and there are a lot of use cases where it's really important to be rather fast when you run something through the command line. You have frequent restarts, you have people working with REPL environments, you have redeployments, you have evals of alien, never before seen code in production environments, like one new line. You can't generate 40 bytecode classes if you execute that all the time. So you have all these pesky scenarios that actually turn out to be quite common. It has to feel fast when you execute from the command line. And optimistic types did nothing to help that. So we have a few things like for an 8214, 8260 that help start up. We have lazy compilation, which is a code generation strategy. I think it's default in Nashorn right now, that only the first time we actually execute a function do we do the complete code generation of it. We have a code caching feature, so you can store both type information and optimistic type information and serialized code, generated code on disk. And for consecutive runs, you can start up faster by deserializing that information. But still, there's a long way to go to get to like your typical native application. You start V8 and boom, prompt is back, right? Even if we completely eliminate all startup overhead in Nashorn, still starting the JVM is significant amounts of work compared to your average native application. But we have to do what we should do what we can do. So optimistic types. I've spoken about this both 2013 and 2014, so those videos are online. So if you want to dive deeper into this in these few slides that I'm going through, feel free to look at the Oracle Media Network for information. There is a JEP number 196 that goes into some detail about how the implementation is done. So what we did there was to attack execution time, and execution time has to do with the invoke dynamic implementation, Java allowing invoke behind the scenes, call sites, because every like fifth instruction, every fifth bytecode or something like that in our generated JavaScript bytecode is an INDI. So it's really important that INDI goes fast. And implicitly and explicitly we'll get boxing everywhere in the libraries, in the representation of generated code, and the VM can do relatively little to actually get rid of this boxing. And also originally, the first Nashorn versions, a function like this that returns a plus b, it was conservative all the way. We can't know statically what a and b are here because the plus operator in JavaScript can handle any object type, numbers, objects, combination thereof. So we generated bytecode that looked something like this, which it's not really important to understand what all the bytecode does here, but we're dealing with a prefixed operators. We're getting a scope object, and we have two dynamic call sites, one that will look up A and one that will look up B. And then we do an invoke static to something called script runtime add, which is maybe 50 lines of Java code correctly implementing the semantics for the JavaScript add operator that takes anything. And anything takes objects here. So even if we do like 1 plus 2, there is an awful amount of boxing going on. There is a call to a very large, way above the inlining threshold function, script runtime add, and lots of cycles to just add two numbers if this is two numbers. So in the optimistic type world, the code will look a little bit different. Still like read the numbers from the scope, but the red lines here are optimistic getters that say, give me an int back, because I assume this is an int, even though I've never seen it before. And if it isn't, throw an exception. Same with B, and then we do an invoke dynamic link to an integer add, which, if we're lucky, will just be an x86 add instruction and a jump on overflow. Because if we're bigger than 32 bits, we can't represent this as a Java int anymore, even though it's still a JavaScript number. And all these guys, all the red optimistic, assume that this is an int operations. They throw an exception if we have the wrong type, or if we overflow, which we christen the unwarranted optimism exception. And so any operation, any optimistic operation in the Nashorn optimistic type bytecode is surrounded with a try-catch handler, method handle combinator, that catches this unwarranted optimism exception. And that in turn takes the local state of the frame of the bytecode method that we're executing In this case, we massage the stack so that nothing is left on the stack whenever an optimistic exception triggers, because when you throw an exception in Java, you lose the bytecode stack. So everything is nicely written to local variables in the bytecode. And every optimistic operation in bytecode is associated with a program point, so we can uniquely identify it when we regenerate the method. I'm just really quickly going through what I talked about last year here, for those who haven't seen it before. And the rewrite exception is thrown to the linker with the local variable state, the frame state, and the linker will generate the rest of the method from this continuation point, make its way out of there. It's basically taking a continuation with the top stack frame, making its way out of there, and then regenerating the method more pessimistically. For example, if this int overflowed, we'll regenerate the method with a double there in its place and call it the next time. So we have this technique for taking continuation when something goes wrong, unwinding the rest of the method, and regenerating a less optimistic version that we call the next time. And by doing this, we can serve up bytecode that is rich in primitives, which Hotspot likes. If you start to serve up bytecode that is boxed everywhere, no VM in the world can help you. It's sad. I would like it to be that way. And there are experiments with escape analysis, but Hotspot is good at executing Java bytecode. That was Java. Alien languages, not so much. So optimistic types really help there. So we use whatever static types there are. It's stupid to throw them away. If we see a static type in JavaScript, or can derive a static type rather from an operation, we will use it. We guess the rest of the types, say that they're ints, and then we have a chain of erroneous guesses that slowly widens the types and causes regenerations of the method. With this continuation mechanism, once it's written and implemented, it's quite elegant and can be used to exit code from a program point, and I'll reuse it for some things you'll see now. So the other thing we have to do is to retain primitive storage wherever possible. If we do an addition of integers and save it to a scope variable, how do we represent the scope variable? Well, the trivial thing would be, the conservative thing would be just to have an object and put a Java-lang integer there with the value. And again, this causes boxing that the JVM can't eliminate. The JVM cannot explode an object field that we use for storage, even if we never store any objects in it other than number objects. So right now we have a slightly kludgy solution that is dual fields, we call it. We're waiting for var handles to appear, and we don't want to use unsafe. So every scope variable in Nashorn is represented as a 64-bit long and an object. And the 64-bit long is used for all the primitive types, double to raw bits, intrinsified for numbers, otherwise truncated or return it to the long if it is 64-bit. So that's really quite fast, and it doesn't cause any boxing for primitive types. So that's the other half of the optimistic type problem. Where do we store scope variables in memory? So we played with tagged arrays and other like sunmisc things that we have some proof of concepts, but we never really checked in any modifications to save memory on this and have a better representation of memory of scope variables in JavaScript and dynamic languages. But I think the var handles are going to help us get rid of this and also eliminate various checks that we don't need for internal arrays and for typed arrays and other JavaScript structures. So I wrote some code actually during jcrete to prove to all the Luddites who say that unsafe needs to be there forever that var handles actually had some performance going, and I was quite impressed with the sandbox branch. For some simple cases, a lot of stuff got eliminated. So I'm a believer in var handles. And the last thing we did for optimistic types is that we have a lot of native methods, which for us is the class library, like the JavaScript array or JavaScript string, whatever, native to us. And they have been, since the beginning in Nashorn, they've been annotated by JavaScript meta-info as an annotation. We implement them in Java. We say that here is mathmax, for instance. It's arity, it's attribute, it lives in the constructor, not in the prototype. And if you want to implement mathmax in JavaScript, it takes an arbitrary 0 or more number of arguments and returns the biggest one of them. And of course, to represent this generically, you have object self, object ellipsis args, boxing, array allocation, deallocation, things behind the scenes. That's really horrible when you just want to like give me the max of 2 numbers, which is the typical use case. There's a lot of overhead to represent that operation That's the special case. The typical case of just doing a math max of 2 numbers, representing it as this is very painful. But JavaScript typically looks like this. The only thing we can say is that it returns a number. That's the only thing, which is a double, as conservative as we can be. That's the only thing the JavaScript spec gives us. So we added specialized functions that basically the linker looks at the primitive arguments that we preserved so well everywhere else, both in scope and in bytecode. And we add an int version that goes to Java lang math max and returns an int that the linker will use if we have ints, and for longs, and for doubles, and for all the other types that we have in the Java language underneath. And then you notice that these take exactly 2 elements because that's the way people use max. And of course, we can add a max which takes 0 elements too, which returns negative infinity. And if someone wants to do that, it's really fast. Just to show the concept of like adding specialized functions that the linker can recognize. So we ended up with some pretty good runtime performance. After warm-up, running the Octane benchmarks, the blue bars there are Rhino, and it's normalized on the red bars, which is Nashorn when we released JDK 8, the first public version of Nashorn. And with optimistic types, we now have the green bars. So we have orders of magnitude of steady state performance, much better than before, because we're careful with our types. And because we specialize, and because we don't widen anything to objects behind the scenes by mistake. But there is a cost, which is the topic of this presentation. I'm doing all my own clip art this year, by the way, because Dr. Buckley put me through so a lot of grief last year with his lawyers. So this is Chili. She will be featured in much of the clip art in this presentation. So startup and warm up until steady state, because being wrong, guessing a type to be narrower than it was, causes a lot of continuation taking and regeneration and class installation. So if we look at the startup time for the Octane benchmarks, it's when do they start executing after generating and executing enough code so they get to this first cycle of benchmarking. If we normalize it on 8U60 with optimistic types, the blue ones, without optimistic types, I mean, and then add optimistic types, basically enable optimistic types the way they are in 9 right now, you see that we have several orders of magnitude longer startup time. And this is just from like you enter a command line for the benchmark until it starts running. So it's even worse because the benchmark payload has to warm up as well. But just like getting to a state where the benchmark starts executing is significantly slower. And
Not wanting to nitpick, but 3 times slower is not orders of magnitude. It's in binary.
yeah, binary orders of magnitude. Several times is bad enough, right? It was slow the way it was, and I think it's slower now. So 2 things stick out here, and those are the 2 nightmare scenarios. PDF.js, which is a really large script, gets significantly slower. So it seems like startup time degrades non-linearly with size of scripts, the number of functions we have to index, not even execute, or but index. So this is one of the, it's not just PDF.js, I verified that this is true for script size in general. And the other one is ray trace, which is a lot of guesses turn out to be too optimistic there. Basically, it works with double arithmetic, and we generate an all-integer benchmark first because we're stupid. We try to salvage as much as we can from looking at scopes and like being doubles, but still we do a lot of regeneration, and that also costs. So those are the 2 prohibitive startup things. We're wrong too often, and the script is large, which also has these trickle-down effects of having us to regenerate things in the optimistic type world. And looking at bytecode mass, classes installed, it's even worse. Because then we normalize the blue one before optimistic types, how much bytecodes, how many bytes of bytecode we generated. And as you can see, it's like 18 times more now for ray trace than it used to be. So this looks scary.
Well, although, of course, need to be clarified that most of that code is thrown away and unloaded.
Yes, of course, but it's generated and installed.
Okay.
So, also when it comes to number of classes that we generate, you also have like several times more. So there are a couple of nightmare use cases. Lots of dynamically evaluated throwaway code, people doing evals that vary on the time they run them, like different evals, different laps and loops and things like that. Relinking hurts us, type invalidation hurts us. just because we have these 9 X's here, scope loads, we do 9 pessimistic type guesses in the worst case, or optimistic type guesses. I mean, we can look at the scope and see that X is sort of a well-behaved citizen and it's the same X, but it's also equally possible in JavaScript that X is like a getter which has global side effects, so that we really have to do 9 recomputations and 9 regenerations and 9 continuations. So this feels bad and nonlinear. So JavaScript is horrible in that X is never just an X potentially, and a lot of the stuff you only know at runtime. So this kind of thing, if you're wrong, and ray trace is full of compound arithmetic expressions where we're actually wrong like this, you grow non-linearly and very quickly in generated classes if you want to use the optimistic typing strategy, which costs you footprint and it costs you startup time, even though, yes, the classes are unloaded and thrown away. And also, I've got some customer cases, some web bug reports. A lot of people who use JavaScript from Java, they end up with this. This is a benchmark that Michelle pointed my attention to. It's about, say, 3 megabytes of Java code, 1 class of auto-generated code that does something with a script engine on every line. Basically, every line is an eval. And they threw a lot of exceptions in this new code. And doing this with optimistic types and say, OK, is this an int eval? OK, it wasn't that. I guess it's a double eval, or just objects here anyway. And same code comes again. We generate it again. There are some outliers that are really bad if you use optimistic types, and every like eval statement here will give you 20 classes. So we have some issues. The performance is really good when it gets stable, but there is some cost because the type matrix part of invalidations makes the number of classes and bytes generated grow non-linearly, and also the script size, because of various optimizations and assumptions, also makes it grow non-linearly. So what you thought was a cute kitten here to the left is actually a really grumpy 17-year-old big cat here on the right, if you don't do some creative surgery. So this is the trickle-down pyramid. You start with JavaScript, which leads to bytecode, which contains invoked dynamics, which contains lambda forms, which, no matter how good the caching is that Vladimir implemented, leads to more bytecode, which leads to class installation, which leads to system dictionary lock, which is very global. And the runtime team say that we will never ever change this. It's not a bug. Alexia is giving them some really nice benchmarks that prove that it's actually very bottlenecky down in the system dictionary if you have a lot of lambda forms, even if they're cached, and they basically say not a bug. So someone else has talked to the runtime team. So this level, the more bytecode you have, incrementally worse things get very quickly. So optimistic types definitely get its runtime performance in steady state, but they make hotspot unfeasibly slow to warm up. And the bigger the method in hotspot, the worse the optimizations. JavaScript methods tend to be bigger than Java methods, and hotspot doesn't do very well with 60K of bytecode. It does very well with 200 bytes of bytecode, but dynamic languages for you. So C2 also is not given linearly increasing bytecode size. C2 has non-linearly increasing compile time as well. So there's various VM internals there as well. But the most, I wouldn't blame C2 for the most part of this. I will blame the installation of huge amounts of bytecode in a non-Java manner. But we can do some optimizations to try to get out of this. Most type guesses are invalidated once. We take one continuation. OK, it was a double. It wasn't an int. It was an object. It wasn't an int. And then they are correct forever. I mean, they won't keep ping-ponging to greater type. So if we just knew the right type from the beginning, if we had static types like my thesis guy, Andreas Gabrielsson, had in his TypeScript front end, everything is so much faster. But that's the entire point of JavaScript, that types are not used. So if we somehow knew the types the first time we start JITting, would we really generate so much new code? And the other one is true for all historic versions of Nashorn as well, that even for call sites that aren't monomorphic, we build sort of an if-else tree of method handle combinators using the object shape, which is called a property map in Nashorn, to check which one of these call sites is the relevant one, depending on the object shape. And this actually gets rid of most relinks, even if we have bimorphic or trimorphic call sites, and it's fairly quick. So it's immensely beneficial for startup time not to regenerate code. Duh, it should be clear, but this is one of the observations that we can make. So let's assume that steady state performance is indeed good enough for now, and optimistic types solve that problem. We now need to attack startup and warm-up time to sort of pay back the huge loan we took out in class generation overhead. And as I mentioned, we've done some previous work with lazy compilation and code caching. That worked well, but don't take us all the way through because, I mean, code caching with optimistic types certainly gets rid of a lot of type invalidations, and you can really feel it in programs that behave sort of like ray trace, where you end up with steady type hierarchies after a long while, but it's still slower. So what would we do without having to write a lot of new code? Could we work with a tier JIT, for instance? Could we do like add a profiling pass to the JIT so we don't generate serious bytecode unless we know the type or unless we have some type profile information? And like make a pessimistic, non-faulting, non-continuation generating, non-bytecode spewing pass in the JIT. That would actually be really simple because very little code would need to be written. Zero code would need to be written, and we can already generate arbitrary level of type pessimism very simply on demand for rewrite exceptions. And if we say that everything is objects, we don't throw any rewrite exceptions, and we can track what type it really is by looking at, is this a boxed number or is this really an object? So also this will lead to no significant test matrix growth as programs would execute the same way with an initial profiling pass. The con here would be the type pollution, because if we work with pessimistic code, like we did the initial versions of Nashorn, we will write to wide values to scopes. We would write Java lang integers to object fields in scopes instead of preserving the primitive. And as soon as you drop the primitive chain from a variable lifecycle in JavaScript, there will be boxing and you're screwed. So it's really important to keep a type primitive. It can be primitive to get performance from the JVM here. So you could probably solve that by like adding return value filters, deboxing stuff, and then you're looking at Lambda forms for them and invoke dynamics and stuff like that.
The same way as it was solved in what we will propose in a few slides. So.
Yeah. And there's a lot of code generation overhead because we didn't get away from the root cause of overhead here. We still have to generate bytecode, a small compile unit, and regenerate it again. We see the system dictionary locks, and bytecode is actually the bottleneck here, which is sad because we generate bytecode and we're a JIT and we're sort of a tier JIT with type guesses. So, and there are also various other class registration horrors, Lambda forms define anonymous classes, and every invoke dynamic leads to a lot of work behind the scenes. So this code generation overhead, having to generate more bytecode, is sort of a deal breaker. We decided after a while there were several ways we could attack this, but it looks like JIT overhead, our JIT overhead generating bytecode is expensive, and we don't get close to like Rhino interpreter startup with the tier JIT approach no matter what we do. And also the type problem that I discussed, we miss optimistic types in scope and have to correct them afterwards with kind of some kind of filters, and it's kind of slow and complex. So our nemesis seems to be bytecode land in this pyramid. Here, more bytecode equals more pain because of the trickle-down effects on the multiplier of what's beneath the bytecode in the JVM. So if we could only emulate and profile the AST before we generate bytecode, collect types and use them for the first JIT if like a method was called again, or just execute the AST until something is hot and only then send it to the JIT. And that's an interpreter on my virtual machine, and layers within layers and wheels within wheels. Is that really, I mean, when we came up with this, it also seemed like a bad thing to do, but we re-implemented everything else on top of Hotspot. So let's try, we just did a thought experiment and did a mock-up and tried to implement an AST emulator, a very lightweight interpreter that basically is thread local, runtime reentrant, and can emulate nodes in the JavaScript AST given a frame, a scope. Something that saves us here is that a lot of the functionality that JavaScript uses is in the script object class and the script runtime class in Nashorn, and is common to the runtime. So hopefully you wouldn't need to generate a lot of code. So what I did is I took the node class, which is the master class for all the AST nodes, and I added an abstract interpret method, which takes a frame, which is the scope we're in, and local variable state. And then I did a very simple interpreter mockup. For instance, the if node. An if is simple to implement. You say that the result is undefined. You use type conversions to Boolean, interpret the test node. If the result is true, I'm using the runtime logic, the slow pessimistic versions that automatically box up my primitives here. Interpret the pass node, get the result. Otherwise, interpret the fail node, get the result, return the result. And these interpreter returns as various wrappers for logging. So it's very simple conceptually to write an interpreter. Control flow is done by throwing various exceptions, like jump exceptions for our inline finalies, a go-to, break and continue exceptions that may or may not contain a label, return exception. It's really pretty trivial to write an interpreter. So a while node. It's probably small code, but I'll put the slides online later. A while node checks that if we have a test and it's not null, while we interpret the test and it's true, interpret the body and catch any break or continue exceptions, and then direct the flow to the correct place by rethrowing it or swallowing it. And we also have an OSR check, and I'm getting to that later, because if we get stuck in a loop and interpreting, obviously this is orders of magnitude slower than executing bytecode even in steady state, we need to get out of there. So it was very simple to plug this into the Nashorn architecture. There's something called a compiled function, which represents one version of a JavaScript or native function with a certain number of parameters that have certain types, like the math max int version would be a compiled function, even though it's native. And it contains method handles for invocation and for the constructor if you create it with, if you call it with new. And it has a certain type, a method type, specialized on params or generic, and a script function data, which is meta info for a function in JavaScript or a native function, has 0 or more compiled functions. So I added a very small subclass to compiled function called interpreted function, which basically represents trampoline. And a trampoline is something that says interpret myself when called. So the call node, which represents a JavaScript call, has an interpret function. When you call that, it will return a script function, and that is really a trampoline. So when you call that, it will bootstrap a thread with the interpreter for that actual function, and that's the way you get into the interpretation loop. So invoke it, and you interpret yourself. So we have the interpret method for all nodes, and it's really maybe 10 to 50 lines of code per AST node. So it's not that much to implement the actual interpreter logic, and the interpreted function, the subclass, the compiled function, is really very small shim class. And the frame that I'm passing around here is an opaque interpreter state, which is local variables and scope, basically. And the scope is the same as the rest of the runtime and uses the same access methods and type functionality and computations as the JIT code would do. So when it comes to calls and stuff, I mean, it would seem likely that we would have to duplicate a lot of functionality, implement link logic for all indie calls, for instance. Linking a call, a getter or a setter, is really complex in Nashorn because of JavaScript semantics. And would you have to implement that in the interpreter again? And there's several things that seem to, all the mathematics and all the operations, would you need to re-implement them? So it seems really infeasible if we were to recreate stuff. But luckily, we can fall back to code that already exists in the runtime part of Nashorn and use the same code from the interpreter. If we do in addition, we can use script runtime add and unbox. It doesn't matter. The interpreter can take time executing as long as we keep its logic down. Because no matter how much time it takes, it's orders of magnitude faster than generating even pessimistic bytecode and installing it and throwing it away. So this enormous soup of code here is like what it takes to link a simple setter, a JavaScript setter, and that in turn has several sub-functions. And we can't re-implement all the logic like that in the interpreter, but it's simple. We can just call the link logic and do the same thing as we would if we saw an indie. Of course, it takes time to look up a call site. And it's creating call sites and method handles behind the scenes, but there are various tricks to that as well. But so it blends pretty well with the runtime logic without generating the bytecode. And I mean, if I had to re-implement everything, all code control logic for everything, it wouldn't be feasible to do this, but the interpreter is actually pretty slim. So there's a few interfaces that basically added get and set methods to things that have getters and setters in JavaScript, and otherwise I implemented the interpreter methods, and it didn't take that long to do. What took long was to get all the special cases right so it could be compliant. But here's an accessor. Again, I apologize for my terribly small fonts here, but if you do get for a.x, which is an access node, this lookup getter thing creates a call site. And the call site is stored in the access node and reused if it's not invalidated. And the lookup uses all the same link logic as Nashorn does in the static code path in bytecode. So it ends up with relatively little new code. And for most logic, we just use stuff that already exists. And even though add is implementing the full sledgehammer script runtime add for objects, we narrow types back, and we have control of types, and we can store a type profile we're interpreting. So very early in the project, we noticed that even if we link call sites, that's probably the slowest interpreter operation. Startup is anyway significantly faster than if you want to go through a bytecode layer. Executing the interpreter code is like 5 to 100 times slower. It's a very jagged graph than executing optimized warmed up written bytecode. So we can't stay in the interpreter for long, but that was never the purpose, because our observation was if we get the types right from the beginning without generating any bytecode or incurring any class installation overheads, we're going to do fine. So we need to transition fairly quickly to JIT code, and time to steady state must also not suffer from this. We can't, even if we execute faster, we still have to stabilize to executing optimized JIT code very quickly. So it seems intuitive that we should collect an initial type profile and throw this away and JIT it. So right now we're using number of invocations as the only JIT metric with no explicit bytecode, but we have like a return value filter on the interpreter trampolines that counts how many times it's been invoked, and I think it's like 5 times or something. We start JITting a code, and then we already have a type profile mapped to the program points that are the same for the AST, no matter if we're going to create code, bytecode, or if we're going to interpret it. So it's deterministic to test, and we're rather aggressive transferring to JIT code. Loops is the special case because you can't keep executing a loop for long, then you're never going to get started. So we're using a rewrite exception there, the same concept that's already implemented in Nashorn for failing a type guess. And what we did was one of these program points that we have to identify optimistic operations. Backage is our program points now too. They fit really well into the program point framework, and we throw a rewrite exception. If we execute a backage too many times, it counts as an operation, optimistic operation that fails, and we transit to JIT, taking continuation with already existing code. So all this code already exists in the optimistic JIT, so it's quite simple to plug it in. So we reuse the program points, as I said. Loop nodes are now optimistic, implement the optimistic interface, which means that they have a program point on the backage. There are some technicalities, stack trace and security. A stack trace is not a special case in JIT code because we generate Java bytecode with line numbers and variables and everything, and it looks really pretty. Just throwing an exception, we'll have the correct JavaScript methods in the stack trace mixed with the runtime Java methods. But if we throw an exception from code executing in the interpreter, of course, we wouldn't see where the code is. We'll just see a lot of node interpret whatever. So we need to rewrite stack trace that are thrown from the interpreter to actually look like the JavaScript code automatically does in the JIT. And that's perfectly doable. It's just bookkeeping. If you have G that calls F that prints A and A doesn't exist, the JIT code would just throw a reference error when it gets to A, and the red parts there, also again, I apologize for the really small font, are 3 JavaScript methods. It's stacktrace.js lines 7, 5, and 2. Doing this in the interpreter won't show you any JavaScript code, but it'll show you several node interpret, the node execute, and something. I mean, it's completely impossible to identify where this exception came from, but we just trap any exception that's on the way out of the interpreter and rewrite it because we have this frame, this concept, this context of what interpreter and what JIT frames we're executing. Both can be on the stack at the same time, of course, and replace any interpreter collections of lines here with the correct JavaScript line number. Only happens on exceptions. It's pretty simple to do. And some native classes need to access the interpreter frame as well for stack trace reasons, because you can manipulate stack traces from error objects in JavaScript, and at least in Nashorn. So the Nashorn tool that takes all these annotations for the native classes has another annotation for passing the frame object in some special cases where we need to. So it's actually quite simple as well. When it comes to security, we need to use the method handle lookups for all call sites that we can reach from the scripts package where the JIT code resides. And if we try to use the lookup that we get from the IR where the interpreter is implemented, it is too privileged. So here is a special case that for every source file we enter, we need to provide a method lookup with the right security level, so we don't try to use a too privileged lookup, or it will be completely insecure. So what we do is that when we enter a new source code that we haven't seen before, the trampoline generates a small bytecode layer, a small bytecode wormhole method, as we call it, that basically writes the correctly privileged, the script package privileged lookup for that source file to the source, and we use that in the interpreter. And as far as I can tell, we can't get out of the privileged domain for that. So the bytecode is like very simple. It just has to generate this wormhole class, which is enter a new source file that we haven't seen before, just marshal the arguments to the real interpreter method and make sure that there is a lookup installed with the correct privileges. And there are various optimizations you can do. I'm almost wrapping up here. So for instance, we can cache call sites. When we have a call site for a getter or a setter or a call, we store that in the node, or we looked it up. But we can also reuse the same call site in the runtime in ways we can't do in the JIT. For example, if we have several nodes that all call G, we can have a scope cache that's the same scope and no invalidations and no side effects have taken place. So we don't need to do another indie lookup, slow link G in the second call site. So we can do nifty little tricks like that and save some interpreter time, which is mostly link time. So we have some caching mechanisms. I messed it up just before I left Oracle, so I think Attila will clean it up and make sure that linking, which is the main bottleneck, but also the main reason we didn't have to write almost any code for this, it works well. So the other thing we have is the program points. It's a problem because when we JIT code in Nashorn, bytecode can only be 64K, so we have to split large methods. We have to do things with finallys, inline them, similar to what Java-C does, and things like that. So we can generate correct bytecode. And if you're interpreting something, you don't really need to generate bytecode. So we don't need to split any code. We don't need to inline finallys. But the problem is that naively reusing the program points for OSR, jumping into the JIT from a loop package, you need to have the same program points as you would if you prepare it for JITting. Otherwise, you can't map a type to a program point or any other information to a program point. So we need to run a lot of the passes that would be unnecessary in something that always interpreted and never moved to the JIT stage. So program points are assigned very late. So given the current representation of program point, which is like a statement in the AST and a position in the AST, we run a lot of transforms that the interpreter really doesn't care about, just so we can identify a program point in JITted code later, when it might be large or split or whatever. So I've experimented a little bit during the summer with a fuzzier program point representation. It's actually, this is not complete, but I'm using the number, the index of the atom in an expression and the position in the source as a tuple to identify a program point. In that case, a program point, the AST doesn't look exactly the same from interpreter mode and JIT mode, but we can still identify a program point because it would have the same index and the same numbered location in the source. There are some issues, but I think it's doable. And then I can avoid running a lot of code transformation passes just to get the AST in a form for the interpreter, so that I can handle OSRs and identify OSR positions in the JIT code. So all these pre-passes like splitting code and computing finallys, I don't really need to do them. A try finally, I interpret that as a try finally in that mode. So there's another strength with two execution environments. We can do background processing, bootstrapping one with the other. We can do speculative JITting in the background. We can even do like multi-threaded speculative JITting in the background. Using futures, I played a little bit with like simultaneously generating several bytecode versions of for different parameter types using futures in the background. Again, this leads to bytecode installation overhead and system dictionary lock, but it's interesting now that we have a bootstrap layer that it frees up a lot of things that were required to be synchronous and dependent on each other before. So the current results with this, the tests are clean. We are JavaScript compliant in interpreter only and mixed modes going to JIT. Startup performance is significantly better than before, and the initial footprint and code generation time is much lower. And it's important to go to the JIT quickly, or it will take longer to reach a steady state with good performance. And type info is usually correct for any program point that you transition. I mean, you need to terror test this, but it passes all the test suites. A JEP is coming and is moving through the process, and I guess it will be made public shortly. And if we look at bytes of bytecode generated during the startup, there's a little green bar that's almost not there anymore. So during the startup, to get to the same position, we're almost exclusively interpreting for the same workload, the same Octane benchmarks that I showed you at the beginning. The little bytecode that we generate are object shapes, classes with a certain number of fields and things like that, but no code, not this early in the game. Crypto has actually started to hand over to the JIT by the time we get to the steady state, but that's the only one. Number of classes generated also shrunk quite significantly, actually shrunk far below what we had even before optimistic types. Well, that's not so hard to understand because we're interpreting. And startup time, it looked like this. This is the one I showed you in the beginning. And now it looks like this. We're actually better than we were without optimistic types to getting to the steady state. So we actually paid back and amortized away more than the cost of implementing optimistic types. And even better, when I do my experimental fuzzy program point implementation, not running these splitting transforms and JIT-only transforms and identifying program points with a slightly more complex algorithm, we paid it way back. The purple bars are low. We're actually more than twice as fast in several cases than we were even before optimistic types, starting up and getting to the same steady state. It's pretty cool given the relatively small amount of code that this interpreter project contains. Ongoing and future work. I'm doing some things for execution overhead that the interpreter enabled. I'm adding some profiling to call sites and allocation sites. If you have this JavaScript code that takes, returns a new array 1,000,000 times and then immediately pushes a string to the array, the current Nashorn will represent this array internally optimistically as an int array, and then it will turn it into, throw that away, create an object array, and do an array copy. So there's overhead, like we'll throw away 1,000,000 int arrays here in this. So what I will do here is, with the interpreter, I know that this program, that what I allocate here, when I change the types of an array, I know where the call site, where the allocation site for the array comes from, and I will tag this allocation site for the JIT that it's no use. I mean, do an object array here immediately. And that's a factor 6 or sometime on this benchmark if you just execute this 1,000,000 times without like having to do the wrong type guess. So I can use the interpreter to create allocation hints in the JIT very simply. I can do partial compilation. I can compile only hot nodes. I don't need to compile an entire method. I can create an add node. I can turn that into a method handle that just does the add. I can specialize that I do with compiled functions. I can have an add for ints as a method handle, the signature. I can have an add for any int and the int17 as a signature. So I can save partial method trees as method handles in the nodes. So if I had the node with the interpret function, you can think of like a small cache of already generated versions of the nodes. So you can build a JIT function from invoking lots of method handles instead of doing one code mass of bytecode when you compute it. So the signature can be an int and an int and the int17. You can add method handle constants, and you can basically have partial evaluation with this approach as well. So we don't need to compile an entire large method. We can just build something out of individual method handles that can also be reused with the typical usual disclaimers of profile pollution. So this is sort of a truffle-style behavior that we can achieve without a modified VM by actually just interpreting and saving the various profiles after they've been JITted as partial method handles. So that's a pretty cool thing that we should look at. And now that Valhalla is coming, we can do the peeks and pokes, but safely. var handles for getters and setters. We can finally get rid of this dual field storage to keep the life of a primitive all the lifetime. We can get rid of bound checks, for example, for our internal spill pool, which is an object array or a long array in the script object with var handles. We can implement typed arrays in JavaScript with var handles much faster than before. So this looks very promising. This stuff I did at jcrete with the sandbox branch, and it looks initially very good. Not the typed arrays, but I'm sure that Alexei will point out what the problems are. So we're doing some JFR integration probably on the future, not going on right now, but we can provide events and JFR integration for any dynamic language toolbox that mission control can consume. And definitely warranted to experiment more with parallelism. With more cores, we can do more speculative jitting in the background and bootstrapping like that. We can improve and speed up Java Lang invoke. There's still boxing going on that shouldn't be going on. The special cases, compile units. Still, when we generate bytecode, the smallest compile unit in Java is still a class with one method in it. And class dynamic, sure, nothing is happening right now, but I think that from Valhalla, the possibility of smaller compile units may spring, which will be very useful. I know that Mikael Haupt has been experimenting a little bit with this. We need some kind of floating constant pole, and maybe we can get rid of like weaving an entire class whenever we want to inject very small amounts of code in the JVM. So research continues for multi-language framework when we have time. We're a bit understaffed, but hopefully we have time. We get time to do this thesis, which should be public. You can Google it. We added a TypeScript front end to Nashorn, and it was fairly pain-free. And other pluggable VM front ends should be investigated. So I guess this puts the end to JVMLS this year. And it's been an interesting spring with all these things, the partial method combination and the interpreter and the insights of that. It was relatively little work to get this there, and that we could pay it off so well, the optimistic types, that we're actually starting faster than we did even before we had it. So this is questions, demos, and beer time. And if you have any questions you can that you think of later, you can tweet them to me or email them to me. My current email is marcus@lagergren.net. And as an homage to Remy, who isn't here, I guess we should end with a unicorn, the chill out session. So that's it. Thank you.